model. Quantum numbers. And we're going to also use these quantum numbers with electron configurations and orbital diagrams, so get a tiny bit of review there for those. All right. Basically, we start off with Schrodinger's model, allowing the electrons to occupy the three-dimensional spaces, those things we call orbitals, and those three-dimensional spaces have a location. We're placing our electrons in different locations in the electron cloud based off of these orbitals. And from the Pauli exclusion principle, we can truly decide that no two electrons have the same 4 quantum numbers. And you didn't know what that meant, but now you're going to know what that means because you're going to know what quantum numbers are. These are their technical names. Principal quantum number, N. Principal quantum number, designated by the letter N, refers to the main energy level, or the principal energy level. On the periodic table, we have 7 rows. Those 7 rows correspond to the 7 energy levels that are there, that are possible. So this number is going to be somewhere between 1 and 7, based off of which principal energy level does the electron reside. The angular quantum number, the second one here, this is an L. It's a cursive L, okay? The angular quantum number is basically saying what is the shape of the orbital. Now you have 4 options here. You have an S, you have a P, you have a D, or an F possible shapes. So there's only 4 possible quantum numbers for this one. And they go from 0 to 3. S is 0, P is 1, D is 2, F is 3. Now we're going to go over this again later in just a minute. The magnetic quantum number, M sub L. So M with the little cursive L as the subscript. This is basically which orbital is it located within the sublevel. So I'm going to show you what that means in just a second. And the spin quantum number, M sub S, this is M sub S, is going to be which way is it spinning? Is it spinning clockwise or counterclockwise? Clockwise is the up arrow, counterclockwise is the down arrow. That's how we represent it in the orbital diagrams. So let's look specifically at each category. We've got quantum numbers, principal energy level, okay? Values, n equals 1, n equals 2, we can go up to n equals 7. Larger values, of course, mean the larger orbitals and farther away from the nucleus. So the principal energy level is going to be this big coefficient number in front of the orbital. So that's energy level 2, this is energy level 1, energy level 3 down here, okay? They're all S-shaped, okay? But the principal energy level is that coefficient number in front of the S, the P, the D, or the F. The angular quantum number, L, the lower cursive L, is going to be the shape. So S is always going to be labeled as a 0. If you're in an S-shaped orbital, you get 0 for that one. If you're in a P, the dumbbell shape, you get a 1. If you're in the D, you get a 2. And if you're in the F block or F sublevel, you get a 3. There's only 4 possible numbers for L. It's 0 through 3, and it depends on are you S, are you P, are you D, or are you F. 0 is S, 1 is P, 2 is D, and 3 is F. Very simply put. Now, this is the harder one, told you. This is the magnetic quantum number, M sub L. Basically tells you which orientation it is. Now for S orbitals only have the one orientation. They are a sphere. There's only a singular orbital in that sublevel. So it's always going to be 0. So this one's always going to be a 0. You'll see the pattern in just a second. The P, though, in the P sublevel, there are 3 orbitals. We have the P on the X, we have the P on the Y, and we have the P on the Z plane. My X doesn't look so good. P on the X, P on the Y, P on the Z. Now, they have three possible orientations. You can be in the one on the X, you can be on the one on the Y, or you can be on the one on the Z. So you can be in orbital -1, orbital 0, or orbital +1, depending upon which one you're assigned to. Okay? So following that logic, we look at D, which has 5 orbitals. What should those ones be numbered as? -2 to +2. Good. So this is going to be -2. This is going to be -1, 0, +1, +2. Depending on which one it falls in for the orbital. And last but not least, for our F's, what do you think those ones are going to be numbered? Correct. -3 to 3. So this is going to be the -3, -2, -1, 0, +1, +2, +3. This one's the hardest one out of all of them, if you ask me, to assign. But you can also look at it this way in the regular orbital diagrams with the boxes. This is how they're numbered, okay? In order to do the, this is what the magnetic quantum number, M sub L. S's are always 0, P's go from -1 to 1, E's go from -2 to 2, F's go from -3 to 3, like so. Last but not least, the spin. This is so easy. The spin's really, really easy. If you're an up arrow, like this, in the box, up arrow, you're spinning clockwise, you are +1/2. That is your designation, +1/2. If you are spinning down in the box, like a down arrow, you are -1/2. That would be counterclockwise. So you have clockwise versus counterclockwise. Clockwise is the up arrow. We designate that +1/2. The down arrow, which would be counterclockwise, is designated as -1/2. So those ones pretty easy. Now let's sum it all up and go back over real quick. The first number is the energy level, and it's always going to be something 1 through 7, because we have 7 energy levels. The angular quantum number is going to be 0, 1, 2, or 3, depending on which block it's in. Is it an S, a P, a D, or an F orbital? The magnetic quantum numbers, remember those ones, S's are 0s, P's go from -1 to 1, D's go from -2 to 2, and F's go from -3 to 3. And then the spin is super easy because we have clockwise is +1/2, arrow going up, and counterclockwise, arrow going down is -1/2. So let's go ahead and practice and do some quantum numbers problems like shown here in the next slide. Oh, I did sum everything up for you in the nice chart so that you can always refer to this as well. In the first energy level, there's only the one sub-level, happens to be 1s. This one. The orientation is 0. The total number of orbitals is 1. Principal energy level 2, you have 2 sub-levels. The orientation, M sub L, goes from -1 to 1. You have 3 possible orbitals for the P. Okay? 1 orbital for the S. The 3 one has 1, 2, 3. So we have a D sub-level in energy level 3. The F's do not come around till principal energy level 4. As you can see, the numbering, just like we just talked about. Okay? This is a good table to refer to. Now, we're going to go step by step through this one. How many possible quantum number combinations are there when n equals 2? Well, here is the second energy level. There's 2 sub-levels in the second energy level, 2 subshells. This is 2s, this is 2p, okay? We're going to go electron by electron and assign them their quantum numbers. So let's start with the first one here. We're going to call this one A, okay? The first electron to fill, okay, it's an up arrow. So A, what's the principal energy level for that guy? That electron? Yes, it's a 2, right? Principal energy level 2. Good. Now, what sublevel is it in? Is it S, P, D, or F? It's in an S. So what number do we assign to the S's? 0. So it's going to get a 0 as the second one. Now, what is the only M sub L or orientation for an S? 0. It has to be 0 because that's the only one there is. And which way is it spinning? Plus a half or minus a half? Spinning clockwise, so plus a half. It's the up arrow. So for that particular electron, that would be the 4 quantum numbers you would assign to it that's like its location or its address. Now let's look at the next one. Let's call this one B. What's the only thing that's going to be different for B? Correct. The spin, it's still in principal energy level 2. It's still in the S orbital, which still has the same orientation of 0. But instead of going up, it's pointing down. So that means it's counterclockwise. That's going to be minus a half. All right, good. Now let's do the next one. Let's call this one C. Okay? What is the principal energy level for C? It is still 2. What is the sublevel though? It is in the P now, so that gets a 1. Very good. Now, let's look at our orbitals here. This is going to be -1, this is going to be 0, this is going to be +1. What is the orientation? It's going to be a -1. Good. And the spin. Which way is it pointing? This is plus a half. Good. Now, last but not least, let's look at this one. Well, not last but not least. This is going to be D. The second one in the P. What's the only thing that's really different between C and D now? The spin, because this one is pointing down. Yes, okay. So it's still going to be principal energy level 2. Still going to be in the P sublevel. A P-shaped orbital. Still going to be in that first orbital, the -1 orbital. And it's minus a half. Very good. Now let's do the middle electrons. Let's call this one E. Principal energy level 2. What should be the second designation number? Also a 1 because it's in the P. But the third one should be a 0. Good, because now it's in the middle orbital. And it does point upwards, like so. So that's going to be plus a half. The one next to it, what's the only difference? We look at F here. Everything else should remain the same. Principal energy level 2, the P sublevel 1, the middle orbital 0, and minus a half for the spin because it's going down. It's counterclockwise. Last but not least, our last 2 electrons over here. We have this one I'm going to call G. So for G, second energy level, P sublevel 1. But what's the new orbital? It's going to be the +1, and it is pointing up, so this one's going to be plus a half. And our last one, next to it, we're going to call H. Okay, so that's 2, still in the P, still in that last orbital 1, but minus a half on the spin because it's going down. So if I had to assign principal energy levels to like something in an orbital diagram, you should be able to do that based on its location, where it's all that stuff. Very good. Now, this could be a different type of question to ask. Like, which one has mistakes or an invalid quantum number in it? So, looking at A, can you spot any invalid quantum numbers? Yes, some of you see it. The n equals 0. That's not even possible, right? Because the n numbers can only go from what? 1 to 7. Very good. So this is incorrect. N is going to go from 1 to 7. We have 7 energy levels. So the n number has to be 1 through 7. Now, as they add more elements to the table, we might eventually have an energy level 8, but right now we don't. So we're going to stick with the 7, okay? L can be 0. What does the L0 tell you? Tells you it's an S. And what does M sub L tell you? It's the one orbital in the S. Very good, right? So those ones are okay. How about B? Do we have any invalid quantum numbers here? What's wrong with the sublevel? I think you're onto something. That one is wrong. But why is it wrong? What does L equals 3 tell me? That it's a what? It's an F, right? It's an F. Does the third energy level have the F's? No. So this is incorrect because the third energy level, guess which ones they have? They have S, P, and D. No F's. So the only L numbers they should have for the third energy level are 0, 1, or 2. Not a 3. However, the M sub L is okay because 1, 2, 3, 4, 5, and a D, you can still have a -2, right? You can still have something in there. So that one's okay. All right, looking at C, are there any invalid quantum numbers? Energy level 4. What does the L tell me? It's a P, that's okay. And guess what? If we're doing a P, it's going to go from -1 to +1. So C checks out. Nothing wrong there. You can be in principal energy level 4, you can be in the P sub level, and you can also be in the -1 orbital. All right, now we're going to do one more set. We're doing a little practice here with quantum numbers. Before we do that, let's review some electron configuration stuff. Okay, electron configuration. Remember, it's the arrangement to arrange the electrons in the lowest energy levels possible, following the Aufbau principle. Okay. Most stable, lowest energy arrangements, we call that the ground state configuration. And we use the periodic table, right? That's the best pattern. Now, remember, the coefficients, the ones shown up there in blue, those ones always represent the main energy level or the period. For the S's and the P's, definitely. For the D's and F's, they're slightly different. The S's and the P's and the D's, those represent the sublevels or the subshells. And the superscript numbers tell you how many electrons are in there. Then you can also figure out the orbital diagram by drawing in the arrows using an Aufbau one like this where it shows you the energies. Okay? But for some, we're just going to draw the boxes or the lines and arrows in a line across. So let's go ahead and do some examples here. Like carbon. What is the electron configuration for carbon? Start at the top. We're going to fill in 1s2 because we're going to go through hydrogen and helium. We're going to go through lithium and beryllium, so 2s2. How many do we go into the 2p? 2. Boron, then carbon. We land on carbon. So that's the configuration for carbon. 1s2, 2s2, 2p2. Now what is the noble gas configuration then? We go up 1 and over, so that's going to be what goes in brackets? Helium goes in brackets, good. Then we start with the row that carbon's in and start adding on the rest. So this is going to be 2s2, 2p2. Now for drawing the orbital diagram. I'm just going to use lines because it's easier. 1s, 2s, 2p. All you have to do is draw that, and then you add your arrows. So there's 2 in the s, 1 up, 1 down. 2 in the 2s. How many arrows go in the 2p, and how do they look? You put 1 in each, following Hund's rule. Okay, now, for the quantum numbers now, we want to assign it to the last electron to fill in the orbital diagram. So the last electron to fill is going to be this one, right? Last one that you put in the orbital diagram. So what are the quantum numbers for that particular one? Energy level, 2. Sublevel, 1 for the P. Orientation, 0, because it's in the middle orbital, right? Middle orbital. Remember, this goes -1, 0, +1. And which way is it spinning? No. Aluminium, yes. Let's look at aluminum. What's the configuration for aluminum? 1s2, 2s2. Good. You keep going until you get to aluminum and you land on 3p1. What is the noble gas configuration? 3s2, neon, because that's the noble gas above 3p1. Now let's draw the orbital diagram. Fill it in. So we fill this in. Everything gets filled in except for the 3p. Following Hund's rule, 1 in each first, then pair them up. Now, which one's the last electron to fill? This one, right? So what are the quantum numbers for that electron? 3, and then it's in a p, so that's a 1. -1, because this is the -1, 0, +1. And plus a half. Good. Try calcium real quick. See if you can do it.
I'm starting to.
Calcium goes, well, where does calcium's electron configuration end? It ends on 4s2, I agree. So I'm just going to write it all down. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Now, the noble gas configuration does help to shorten this down. What is this one going to be? Argon and 4s2. Very good. That's nice and easy. Yes. Now, orbital diagram. 1s, fill that in. 2s, fill that in. 2p. 1, 2, 3, 4, 5, 6. 3s, 1, 2. 3p. 1, 2, 3, 4, 5, 6, and then 4s filled. Now the last electron to fill is going to be this one. So what are the quantum numbers for that particular electron? That's going to be 4. Good. Principal energy level 4. And it's in an S, so that's going to be 0. Then comes S orbital orientation as always 0. And which way is it spinning? -1/2. The last but most complicated one of the bunch is copper. So let's go ahead and do copper real quick, because copper lands in the D block. So what does copper end on? Let's count. Copper over here on the periodic table. 1, 2, 3, 4, 5, 6, 7, 8, 9. Lands on 9. Thank you. So I'm going to go past calcium, the 4s2, and I'm going to add on the 3d9. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. Now what's the noble gas configuration for this one? We still go up and use argon, good. And what do we have to add on the end with the row of copper? 4s2 and... Okay, so remember where those noble gas configurations come from. Like this part, 1s2 to 3p6, that's representing argon. Argon is that configuration, so that's why we can insert argon at that point. Now for the orbital diagram. 1s, you might have to go below the line if you run out of space. 2s, that's easy. 2p, 1, 2, 3, 4, 5, 6. 3s, 3p, 1, 2, 3, 4, 5, 6. 4s. Now for the 3D. 1, 2, 3, 4, 5. Notice where it gets a little complicated as to the last filling electron. You have to put one in each first, right? Hund's rule. One in each first. So that's 5. This is 6, 7, 8, 9. That last one I put in is the last one to fill. So the last one to fill happens to be this one right here. You have to follow Hund's rule on that, okay? So what are the quantum numbers of this last down arrow here?
3.
Principal energy level 3. What's the sub-level now?
2.
It's a 2 for D. And what's our orbital? Remember, this goes -2, -1, 0, +1, +2. So this is going to be +1, and then it's spinning down counterclockwise. Yes, -0.5. So you'll see a few of these example problems in your study guide. Make sure you work on your study guide and prepare for Kahoot.